Hello, my name is Noah Sanz. I'm here with Penny Xiao, Brendan Powell, and Jacob Totri, and we are presenting our analysis of an internal combustion engine. Generative Energy Systems Incorporated designed this combustion engine and have asked us at Burdell Incorporated to help them characterize the system and develop a controller for it. To study the engine, it is connected to a 48-volt regenerative motor that can be used to power the engine or to generate energy when powered by the engine. An optical encoder is used to measure the radial position of the motor and the engine shaft, and a force transducer is used to measure the torque of the shaft. Using the encoder data, the position of the piston and the speed of the engine can be determined. Using the force transducer data, the effects of friction on the system at various speeds can be observed. By running tests and recording data such as shaft speed, shaft torque, and frictional torque, the inertia of the shaft and its components inside of the assembly can be calculated. Additional testing can be used to define the relationship between the engine's flywheel and the pressurized air within the engine. With the engine characterized, a controller can be made to ensure the engine can maximize its power generation. To begin testing, the IC engine is attached on a shaft to a 48-volt regenerative motor. It is also equipped with an RLS RM58 AC analog sinusoidal encoder to measure the shaft position, and a force transducer to measure the shaft torque. Mass measurements are taken using a Sartorius 3862 MP8 electric mass scale, and length measurements are taken using a ruler. An NI Elvis 3 DAQ board is used for time and voltage measurements, including the force transducer voltage. Before testing begins, the force transducer must be calibrated. This is done by taking voltage measurements from the force transducer with known amounts of torque on the system. This known amount of torque comes from adding weights to the end of an arm attached to the shaft. The weights are measured on the mass scale and the arm is measured with the ruler. Voltage data is recorded with no weights, then with one weight, then with two, and so on until 6 weights are reached. After recording the voltage at 6 weights, a weight is removed and another data point is taken. This is continued until all the weights are removed. By taking measurements both while adding and subtracting the weights, the effects of hysteresis on the system are accounted for. Using the recorded voltage data and the torque data calculated from the weight and arm measurements, the Elvis board can calibrate its force transducer measurements. With calibration complete, tests can be run at different speeds and different flywheel rates. Weights. Using speed and torque data, the inertia of the shaft and all of its components can be calculated. This can be compared to the theoretical value for the shaft's moment of inertia to determine the effects of friction on the system. Similar testing can then be run on the engine with the engine head attached. This introduces compressed air to the previously characterized system. By analyzing the engine at different speeds and flywheel weights across the full 4-stroke cycle, the effect of this pressurized air on the flywheel can be calculated. With the internal components and forces of the engine characterized, testing can be carried out at various voltages and injection angles. By analyzing the results of these tests, the minimum working voltage for the engine can be determined, as well as the optimal power generating conditions.
Hi, my name is Jacob Totri. I'd like to discuss the mechanical properties of our internal combustion engine based on our experimental findings. To characterize the frictional properties, we measured the torque of friction at different engine speeds, ensuring that the engine reached a steady state before data collection. We found that once the engine reached a steady state, the torque of friction remained relatively constant. This means that the area under the torque versus angular position curve represents the work done by the frictional forces. We believe that the work done by friction is the main counteracting force to the power input from the engine. By dividing the moment arm, we were able to calculate the work due to friction. During our analysis, an outlier point emerged, leading to a negative moment of inertia for the specific data point. We consider this an anomaly and will further investigate it to ensure the accuracy of our calculations. Moving on, when we removed the flywheels, we observed changes in engine acceleration, highlighting the crucial role of the flywheel in maintaining steady operation and overall system performance. While most of our modeling assumptions held up well, this outlier highlighted the need for further investigation and refinement. These findings provide valuable insights into the mechanical properties of our IC engine, aiding in the optimization of performance and efficiency. Thank you.
With a linear relationship between torque due to friction and the motor speed from results 1, we are able to use equation A to find the moment of inertia of the system based on its relative speed and the amount of flywheel on the motor, as seen on the table on the left. Using equation B, we are able to find the moment of inertia of each flywheel segmented by the relative speed, as seen on the table on the right. Keep in mind that at moderate speed, the moment of inertia of each flywheel is calculated to be negative. We will further discuss this in the next slide. Since the moment of inertia calculation for one flywheel at moderate speed have produced a negative moment of inertia value, an error propagation analysis will be performed with the following uncertainty and moment of inertia equation listed below. With the uncertainty values calculated for the moment of inertia of each flywheel at its own relative velocity, we can see from this graph that the raw data has error bounds that encompasses the theoretical value. This means that all three data points are valid even though at moderate speed the moment of inertia was calculated to be negative. However, we will be omitting the data point at moderate speed just because we only have 3 data points. This has resulted in us obtaining a I-average value for each flywheel to be approximately 0.0028.
So, having characterized the friction and moment of inertia of various system configurations in the previous steps, the next objective is to investigate the engine's behavior with the head on. By mounting the head, the work due to the air inside the cylinder becomes non-zero. At this point, the inertia of the flywheel, angular velocity, work due to motor torque, work due to friction, and work due to the piston have all been evaluated experimentally. This allows for the work due to the air inside the cylinder to be isolated and solved for as shown by the equation below. The engine will be run at 3 different speeds with 2 configurations of flywheel weights. The data collected from these trials allows for a full 4-stroke cycle analysis that will produce the work due to the air during the compression stroke and expansion strokes. The data will encompass multiple full cycles, so the data can be segmented and averaged to generate a representative cycle for the system. For comparison, the engine operation can be modeled as an air standard Otto cycle at wide open throttle. A diagram of the cycle is shown on the right, courtesy of Engineering Fundamentals of the Internal Combustion Engine from Polkerbret. Under this model, the intake and exhaust strokes generate no work since the pressure is constant. The isentropic compression from points 1 to 2 and isentropic expansion from points 3 to 4 can be used to solve for work due to these respective steps of the 4-stroke cycle using the fact that work is equal to the integral of PdV. The experimental values should differ from the calculations generated from the model, but they should be comparable. With no energy added during isochoric combustion and exhaust blowdown, it is expected that the work from the compression stroke should be about the same as the work from the expansion stroke. Next up, energy can be added to the system in the form of pressurized air injected at top dead center to simulate isochoric combustion. This will cause energy to be added to the system, thus allowing the engine to generate more work during the expansion stroke than it utilizes in the compression stroke. The result is a net work output, which, over multiple cycles, becomes power generation by the system. This power will be determined experimentally to find the minimum running speed and maximum power output of the engine, which allows for determination of the optimum configuration for generating power from this engine. On behalf of Burdell Incorporated, we thank you for taking the time to view our progress, and we look forward to providing valuable insight to GESI's internal combustion engine endeavors.